Hi everyone, my name is Mu Cai, final year PhD student from University of Wisconsin-Madison. Today I will present our WACV2025 paper, an investigation on LLMs visual understanding ability using SVG for image text bridging. This is a joint work with UW-Madison and UIUC. Here I also attach the paper link. As the title indicates, we are working on image text bridging. Then an intriguing question is, how do current multimodal models work? Most models currently they translate pixels into a set of visual tokens, and then language model can understand the image. As you can see here, this is a classic vision language model architecture, lava style models. But then, can we really think out a way that we can directly embed visual information onto the text space? That being said, we will no longer need the vision encoder and vision language connector, and we need to think out a way to directly translate the images into the textual input space. The first choice is very natural. Can we use real pixels to represent it? The answer is definitely no. Why? Because firstly, the sequence will be prohibitively long, and secondly, there will be no semantics from such low pixels. This tells us that we need to find a way to simplify the image and also provide the semantics to language model. Luckily, artists like Picasso give us some hints. So as this image indicates, Picasso tried to convert images into very simple sketches, and finally people can understand that Picasso wants to express that this is an ox just from several sketches. Can we also find a similar representation in computer vision? Luckily, in computer vision, we do have such a format. Our key idea is to leverage Scalable Vector Graphics, short for SVG, in our paper. So SVGs are defined in XML format and use mathematical equations to depict shapes, curves, lines, and color. As you can see from the image, one golf course can be decomposed into several geometry primitives, and each geometry primitive will be described by one code block. Here, the code block will include key information such as color and object shape. When you see this new image, you should pause the video and think about what's the difference between this image and the image in the previous slide. After some seconds, you will realize that the black circle in the middle is missing. So why it's missing? Because the corresponding code block has been commented. And this tells us that SVG is just the collection from a set of discrete components, and users can edit SVG in a text editor. If you are working on multimodal but tired of pixels, I strongly recommend you to check out vector graphics. Compared to rasterized representation like PNG, SVG have several mirrors. For example, PNG will represent the visual content in a fixed resolution, but SVG has infinite resolution. Also, as we all know, PNG is very hard to do image manipulation, but for SVG it's very easy, just as the previous slide showed. And finally, PNG is very easy to lose fine details because the nature of its fixed resolution. But SVG can actually be widely used in cartoon or science because of the feature of infinite resolution. For image representation, PNG will use pixels to represent, but SVG will use code blocks to produce infinite resolution. For image generation, PNG format will usually require heavy models like diffusion model to generate the image with a lot of time steps. But for SVG, we can actually generate images and even edit images in a dialogue with a textual-only LLM. For image understanding, PNG format usually require some specific architecture like ResNet or transformer in order to extract the features. But again, for SVG, we can use LLM to do dialogue style image understanding. In this paper, we will show several cool aspects of SVG, including shape bias robustness, enhanced image classification, and also interactive image generation and editing capability. So what kind of architectures do we require to understand SVG? Different from PNG, which need a vision model like convolutional neural network or transformer to understand its content, SVG just need a language model to understand both the input and also generates the response in the same textual format. We leverage different sources of data set to understand this problem. Firstly, we use a human-designed SVG dataset, including icons and numbers. In addition to this, we also include real-world images, which we will convert the rasterized representation to SVG format. Firstly, for simple images, we just simply use curve tracing to get the resulting image. In addition to this, for complex images, we first leverage segmentation prior, like leveraging SEM model, and then use the curve tracing again to get the SVG representation. For image classification, we consider two settings. One is a zero shot. Another is in-context learning, where we will provide several examples in the context. We found that on capable models like GPT-4, with the number of in-context learning samples increasing, the accuracy will gradually increase. Definitely, the classification accuracy of GPT-4 on MNIST SVG format is far from perfect. So we further explore the limit of SVG representation by fine-tuning Vicuna, a language model, on the training set of MNIST. Results tell us that SVG format using Vicuna can actually achieve higher accuracy compared to a ResNet 50 on PNG format. Here we further challenge such models under distribution shift, where we curate color MNIST from MNIST but with diverse background and foreground colors, resulting in colored MNIST A and colored MNIST B, which is harder. Results tell us that SVG format shows stronger robustness towards debasing color from shape, as you can see from the green bar. So under both color MNIST A and colored MNIST B, SVG format is much better compared to baselines using rasterized representation. So let's understand why this is happening. Because if you closely look at the SVG code, SVG on explicit shape color disentanglement, where changing the color will not affect the performance with respect to shape. In addition to image classification, we also conduct experiments on visual reasoning, and we found that SVG can actually perform better in visual reasoning. Here we use a sort of clever dataset, which includes three kinds of questions. The first category is unary, the second category is binary, the third category is ternary, where the level of difficulty gradually increases. You can pause the video and closely look at what kind of questions those three categories denote. As the table and figure show, SVG representation again show benefits compared to PNG representation. As you can see here, when GPT-4 combined with chain of thought technique, denoted by the dark green bar, it shows better performance than the baselines PNG format. This again tells us that SVG has strong potential in visual reasoning. We also introduced a new SVG VQA dataset where we found that capable models like GPT-4 shows a certain level of VQA capability. Now let's come to the image generation and editing side. We found that LLMs can actually understand and generate SVG code. As you can see from this visualization, GPT-4 can actually colorize the color and really do some editing stuff such as make the skin brown. To quantitatively study this behavior, we first conduct a synthetic data study where given two example pairs and a query SVG, GPT-4 need to figure out the common transformation and transform the query into the corresponding key, as you can see from the visualizations. Surprisingly, we found that GPT-4 with SVG representation shows near perfect performance compared to baselines with rasterized representation. Here we can conclude that GPT-4 can clearly understand simple shapes, color, and size transformations and analyze the SVG code without any pixel level information. Here is another style generation task, where the model needs to figure out the style in the given example and transform the query SVG. In this dialog, we can observe that with continuous dialog, GPT-4 can improve the SVG generation quality. Here we introduce another task called content generation, where the model needs to figure out the mathematical operation in two given examples and transform the query SVG. Here, the qualitative results tell us that GPT-4 with SVG format is really smart, right? For example, when we just provide Wang query 21 and Wang key for 14 and just give the test query 12, GPT-4 can smartly detect that the answer could be either 8 or 5. We also have interesting experiments such as referral segmentation for real-world objects. Please also check our open-ended chatting examples and more dialogue-based visualization. However, our approach do have limitations. Firstly, SVG could lose details for photographic content, and secondly, when there are many details, SVG sequence could be prohibitively long. For example, for the right side cat. Quantitatively, it means that 10 datasets tell us that SVG format receives a much lower accuracy compared to the resurrect representation. So an intriguing future work is that can we build a hybrid representation that we can enjoy the benefits of both SVG and PNG format. In conclusion, SVG is a shape-biased representation which enjoys the benefits of in-context learning and image generation capability, but it loses details for some natural images. Thank you. If you have any questions, please send me an email.